Today we're going to be talking about something you guys have heard before, which is the DFT. So that sounds an awful lot like the DTFT, but it's not. This is the discrete Fourier transform, not be confused with the DTFT, which is the discrete time Fourier transform. And we'll talk about what this means from an intuition standpoint, how to do it by math, and how MATLAB handles it too. So I think it's best to start talking about, of course, the intuition behind it. And let me begin by giving you an example sample. So here's a short finite length sample, and we feed that into our DTFT. So this is what we've already talked about. And our DTFT takes a real sequence in, and it pops out a complex sequence. So I can't graph the whole thing in its complex wonderfulness, but I can graph its absolute part, and I can graph its angle part, its phase part. And Gordon, is the DTFT, it takes a discrete signal. Does it put out a discrete or a continuous signal?
Should put out a discrete, sir.
No. So the DTFT puts out a continuous signal in omega. So omega is varying smoothly between 0 and, well, uniquely pi, but it goes up to 2 pi or 3 pi. It goes negative also, down to negative pi and before. So for this particular signal, there's definitely something changing in it, but it looks to me like it's not changing rapidly. It's not going between +5, -5, +5, -5. It's mostly low frequency energy. So if I was to graph what that looks like, it might be something like that. And Gordon, if it looks like this between 0 and pi, what does it look like to the right of that, between pi and 2 pi?
Should be reflected, sir.
That's right. And that's my best reflection. And it continues on like that too, right? It goes on and on like that in both directions. So the DFT is a discrete time signal. And it's a discrete time signal out of the same length as a discrete time signal in. So it's going to have just 4 points in it. We'll call it capital X, and this time we'll call it of K, where K is our discrete time integer. It's not N. We use N traditionally for time domain, and we use something else like K for frequency domain. And what it is just a sampled DTFT. It'd be wonderful if it's sampled between 0 and pi, but instead it's sampled between 0 and roughly 2 pi. And it's not even that. It's 1 sample less than 2 pi. So in other words, if it had 4 samples in it, these would be the 4 samples. And then it would be as if the 5th sample would be at 2 pi. So in other words, it would look like this. And now we're going to count it using integers. Let's do one more. If we take this exact same sequence, except now I'm going to 0 pad it. And I'm going to put that through my DTFT. Nick Howsand, tell me what you would expect its DTFT to look like. How would it look, similar or different to the one we graphed above, to this one?
It would look the same.
It'll look exactly the same, that's right. Between 0 and pi and 2 pi. It'll look exactly the same. It's the same, as far as the DTFT is concerned, it's the same sequence because it's taking the sum over all infinity of points. So the fact that these are zeros will just multiply it by 0, just like over here would be multiplied by 0. Now, Jeremiah, tell me how that is going to be different than what the DFT of that sequence is going to look like.
It's just going to have a higher sampling rate because there's it's a larger length on the input.
Exactly. Oh, and something I should have said before is that the DFT truly is just a sampled DTFT. So it's also complex. So I should have drawn the magnitude signs over here. And so now we're going to sample this thing twice as often. And this is the one at 2 pi that we're not going to quite sample. So this would be if we had 4, but now we've sampled it more completely. So now our DTFT looks like this.
And so that's a useful use of zero padding in general.
That's the point exactly. That's where we use zero padding because we'll get a better approximation for what our DTFT is. Oh, and just notice that this is a length of 4, even though its highest index is 3, right? It always goes between, our finite length signals go in general between 0 and n minus 1. So this is this lower one has an n of 8, and so it goes again between 0 and capital N minus 1. All right, so yeah, exactly. This is a useful function of why you want a zero pad, so your DFT can more closely approximate your DTFT. But then my question is, well, why the heck even have a DFT? If we have our DTFT, that's perfectly sampled. That's a perfectly continuous function. Why go through this mess of having a DFT and then having to zero pad so we can approximate the DTFT, which is what we want? And the answer to that question, the DTFT, is hard to compute. You can do it by hand, but it's not easy. The DFT is easy to compute. In fact, there's a special algorithm to compute the DFT that was discovered in the 1960s. And that algorithm is called the FFT, the Fast Fourier Transform, which is a complete misnomer because the FFT is not a transform. It's an algorithm, and it's an algorithm to compute the discrete time Fourier transform. It's an interesting story. It was developed by Cooley and Tukey in mid-1960s, and it really revolutionized digital signal processing. It created the whole field of digital signal processing. It's being able to compute the DFT rapidly that makes digital signal processing a field. And then after it became popularized, it was discovered that Gauss had discovered the same algorithm 200 years earlier, but because they didn't have computers back then, no one really picked it up for what it was.
Sure, I have a quick question.
Shoot.
I just don't understand, under your intuition, how your X of n corresponds with the DFT graph. Like it's 1, 2, 3, 4, but like.
Okay, do you understand how the X of n corresponds to the DTFT graph, this top one?
Yes, sir.
Good, okay. So all we're doing is we're sampling the DTFT. So if our input sequence is 4 long, then the DTFT is a continuous graph. It has an infinite number of points, but our DFT is discrete. It will have the same number of points as our input sequence. So if our input sequence has 4, our DFT will be 4 long, and it will be 4 samples, evenly spaced samples of our DTFT. And the trick is that it'll be spaced in such a way that if it was one more sample, if it was a 5th sample, it would evenly sample the DTFT between 0 and 2 pi. So here's our 4 samples of the DTFT, such that if there was a 5th, it would be exactly at 2 pi. And now we've zero pad to make it longer. And now we're going to evenly sample the DTFT 8 times, since our input sequence is 8 long. and we'll sample it such that if we were sampling it at 9 samples, the 9th would correspond to 2 pi. Does that make sense?
Yes, sir.
Yeah, it's a good question, and it's important to get that intuition now. If you get the intuition, the math is easy. So the intuition is that for a DFT, a sequence in yields a sequence out. So different than the DTFT, where a sequence in yielded this continuous function out. And that means it's perfect for MATLAB, or really any kind of computer. Yeah, shoot.
So a good way to visualize it, am I wrong here by saying, so like it encompasses the DFT the DFT encompasses every point but 2 pi, but that includes 0. So if you repeat that same sampling process, you get the full frequency waveform every time, or like
that's right.
Yeah.
And let me say what you just said in a slightly different way. These points will be complex conjugates. If you know what this point on the left is, you know what the point on the right is, just take its complex conjugate. So therefore the magnitude which we drew would be the exact same. These 2 points will be complex conjugates. These 2 points will be complex conjugates. And then this point doesn't exist, but if you wanted to try to recreate it, you could. And so in some ways that means that you've got, you're saying that much of the DFT when it's computed is actually unnecessary. Roughly half the points are unnecessary, right? These points, all those points don't provide any extra information. And that's roughly half. Sometimes the way you sample it, sometimes it includes this middle sample, sometimes it doesn't, sometimes it's on either side of the pi, depending upon if n is even or odd. But for a large n, when n is in the millions and tens of millions like you often get, your DFT will have half of it will be unnecessary duplicate information. And that is true. If you're feeding it a real n, as long as this input sequence is real, these will be complex conjugate values of each other. And for what we do, x of n will always be real. Does that answer your question?
Yes, sir. Thank you.
Sure. So x of n, little x of n in the time domain, big X of k in the frequency domain, it's the DFT. They are both, I know I've said this before, but I just want to hammer this in. They are both finite length. And how finite length? Length n. And so n or k will both go between 0 and capital N minus 1. And just like the DTFT, x of n is associated with exactly 1 capital X of k, and capital X of k is associated with exactly 1 x of n.